That ghostly smudge might outweigh a billion suns, yet barely shines. Immediate takeaway: some galaxies are almost pure dark matter. Mass is there, while light hides like embers under ash. Astronomers call them dark matter-dominated galaxies, which is wonderfully literal. Why care about these faint ghosts drifting at the edge? Because they strip the story to gravity and fuel. You watch how halos rule when star-making sputters or fails. Mechanically, a heavy dark halo forms first, like a deep well. Gas tries to fall in, but heating and winds push back. Nearby giants tug, while ram pressure scrubs anything loosely bound. Result: a huge skeleton of mass with almost no flesh. Dragonfly images show cotton puff galaxies about Milky Way size. Yet their starlight totals only a few 100 million suns. Early numbers for Dragonfly 44 hinted at 99% darkness. Later estimates dropped that, but the halo still commanded things. Bottom line: you can build a massive frame with barely any light. One sentence recap: heavy wells can host feather-light stellar glows. That mismatch is the clue, not the bug. You lean into the eyepiece and a cloud fills your view. Big across the sky, yet barely brighter than the background. A dark matter-dominated galaxy means hidden mass outweighs luminous matter. Stars are garnish on an enormous invisible halo. Care, because these ghosts stress test how galaxies actually assemble. If they exist widely, our recipes must handle dim outcomes. Gravity builds the arena, while star formation sometimes never takes stage. Here is the play in clear steps, minus the mystery. Dark matter collapses early, creating a deep, stable gravitational well. Gas falls inward, shocks and heats to hundreds of thousands degrees. Cooling stalls, while supernovae punch holes that vent remaining fuel. Neighbors tug, and hot environments strip anything loosely held. Observers then weigh the ghost by tracking motions and distortions. Stellar jitters set a velocity dispersion, quoted in kilometers per second. Globular clusters orbit like bees, sampling the halo far out. Example: in real terms, ultra-diffuse galaxies can match Milky Way diameter, yet they hold only a few 100 million suns in starlight. Dragonfly 44 first looked extreme, near 99% dark matter. Later analyses reduced that share, yet the halo still dominates. These systems stretch surface brightness to the edge of detectability. You need long exposures, careful backgrounds, and steady calibration stars. Tiny tests blur the image slightly, and the galaxy disappears. Net result: a huge halo carries a whisper-thin stellar fog. That is why these targets feel like balancing on darkness. Move the sky model slightly and your measurement swings wildly. Still, the physics repeats, which builds confidence across surveys. Different teams recover similar masses from entirely independent tracers. So the picture holds, even when details shift a bit. So what is this dark matter that refuses to glow? It is mass that pulls, yet ignores light and electromagnetism. We care because it sculpts galaxies, clusters, and the cosmic web. Without it, several bedrock measurements break in uncomfortable ways. Rotation curves would fall, while they actually stay puzzlingly flat. Gravitational lensing would weaken, yet it remains impressively strong. The microwave background would shift, which it stubbornly does not. Mechanically, dark matter interacts mainly through gravity, and perhaps weakly. It clumps early, creating halos that shepherd baryons into structures. Baryons radiate energy, cool, and feel feedback from violent events. Halos deepen slowly, while light struggles inside those changing potentials. Lensing bends background galaxies, drawing mass maps like contour lines. Rotation stays flat far out, where stars alone cannot suffice. Satellite swarms orbit faster than visible mass can comfortably allow. The bullet cluster adds a striking, almost cinematic separation. Hot gas smashes together, lights up, and lags behind the galaxies. Lensing peaks sit offset from the gas by hundreds of kiloparsecs. That offset says the heavy matter barely collides, then sails through. Simulations with dark matter reproduce large-scale structure with eerie fidelity. They paint filaments, nodes, and voids that match survey maps. Change the recipe, and those patterns drift away from reality. One-sentence recap: halos are scaffolds, while starlight is decoration. That is why dark-dominated galaxies feel so revealing. They let gravity speak, almost without baryonic complications. With fewer moving parts, the test becomes much cleaner. So the evidence chain tightens, link by careful link. Now switch to a small galaxy skimming past a giant neighbor. Tides grab the outskirts, and long streams start peeling away. A mostly dark remnant can emerge after repeated close passes. This matters because starlight leaves faster than deep halo mass. At pericenter, differential gravity shears stars from the vulnerable edges. Hot halo gas of the giant also rams the satellite. That ram pressure scrubs loosely bound gas, reducing future star formation. Supernovae inside the dwarf add kicks that help losses grow. The central dark halo still grips tight, protecting the core. Over orbits, the dwarf fades while its dispersion hardly budges. Meanwhile, the host collects shells, loops, and curving tidal ribbons. Example with numbers, a satellite might lose 90% of stars. It could still keep more than half its halo mass. Observers would map streams spanning hundreds of kiloparsecs across space, yet the remnant shows a dispersion near 20 to 30. That speed scale implies a deep well beneath the dim light. Common mistake is assuming faint always means intrinsically tiny. Tides can spread light thin without shrinking the true mass. One sentence recap: stripping makes heavy ghosts and gorgeous debris. You can even trace the orbit by the stream geometry. Sharp turns mark pericenters, while diffuse fans mark apocenters. Metallicity gradients along streams reveal where stars originally lived. Spectra then tie those pieces back to the fading core. Every fragment becomes a breadcrumb for the galaxy's past. Follow enough crumbs and the reconstruction becomes surprisingly precise. So the process explains dim giants near aggressive hosts. Switch scenes to a massive halo catching gas at high speed. Shocks at the virial radius heat inflow to extreme temperatures. A failed galaxy is born when star making barely starts. In plain words, the well is deep, while lights stay weak. This matters because quenching can start from the very beginning. Shocks at the virial radius heat inflow to extreme temperatures. Cooling times stretch long, sometimes longer than a Hubble time. Reionization bathes small halos, keeping gas warm and easily lost. Supernova winds then push leftovers outward into the circumgalactic medium. Meanwhile, the dark halo deepens gently, like a slow tide. Star formation flutters, flickers, and never builds a dense disk. Consider a halo near 10 to the power of 11 suns. Its stars might total about 1 billion suns in light. That is roughly 1% stars, with nearly everything else dark. Gas remains hot, diffuse, and hard to settle into clouds. If a neighbor appears, ram pressure scours even that reservoir. Ultraviolet backgrounds raise the floor, preventing easy cooling across epochs. Metallicity stays low, which further hinders efficient radiative losses. Radio maps might find a whisper of neutral hydrogen remaining. Optical images reveal a giant, featherweight, powdery disk. Bottom line, some galaxies are born tired inside oversized wells. These systems look calm, but their early history was loud. Energy injections happened fast, then left a long-lived imprint. They are time capsules for heating and reionization in action. Catch them and you catch a fossil from cosmic dawn, so the channel explains darkness even without violent neighbors. Heavy halos alone can stall the lights for billions of years. Okay, how do we weigh ghosts that barely emit photons? We listen to motions, and we watch how light bends. Velocity dispersion is the spread of random speeds in tracers. Deeper wells demand larger spreads to keep tracers bound. Spectrographs red Doppler shifts from faint absorption lines in stars. For dim systems, observers target globular clusters as bright beacons. Those clusters sample the potential far into the outer halo. Fit their speeds and the mass falls out cleanly. Weak gravitational lensing stacks many frames to see average halos. Galaxies behind get stretched subtly, like rubber under gentle pull. Radio arrays map neutral hydrogen to trace rotation where possible. Each method cross-checks the others, taming tricky systematics. Numbers help, so picture 12 clusters with 32 dispersion. That speed implies a mass more giant than the light suggests. Add lensing shear consistent with a massive, extended halo. Add H-high rotation holding flat out to 20 kiloparsecs. One sentence recap: motion plus bending equals a weighed invisible scaffold. Common mistake is trusting one tracer without environment context. Tides can inflate dispersions, so membership checks matter a lot. Foreground stars sneak in, masking the true velocity spread. Analyses now model contamination, anisotropy, and projection effects carefully. Results still point to halos dominating the budget convincingly. Overlay a simple rule: dispersions near 30 flag deep wells. Below 10, you likely mismeasured, or tides are confusing things. So careful surveys revisit targets until the numbers stop changing. Then come the rebels rumored to lack dark matter entirely. The The claim says stars alone explain the observed motions. People cared because that would challenge decades of converging evidence. Alternatives to dark matter would roar back into serious debate. Several issues likely fueled those early surprising announcements. Distances were uncertain, so sizes and masses were misjudged. Background galaxies snuck into samples and corrupted dispersions subtly. Tides from a giant neighbor can peel outer halos selectively. The remnant then looks light, while true mass sits elsewhere. Once distances improved, mass estimates rose by notable factors. Revised dispersions landed between 10 and 20 kilometers per second. Membership checks dropped imposters, tightening the sample considerably. Specific case DF2 and DF4 orbit near the NGC 1052 group. Early reports suggested dispersions near 8, hinting at missing halos. Later work pushed them farther away, increasing inferred masses. Follow-up also found tidal features consistent with interaction history. Bottom line, true zero dark matter galaxies remain unproven and unlikely. The lesson is humility with distances and membership in cluttered fields. Independent methods should agree before we claim an extraordinary case. Extraordinary claims require carefully boring, reproducible measurements. So far, the boring answers have kept winning decisively. Step back and watch the universe as a tangled dark web. Dark-dominated galaxies live in clusters, groups, and quiet voids. Environment decides who keeps gas and who loses fuel. In clusters, hot atmospheres and tides erase light with enthusiasm. In voids, slow trickles starve clouds over very long timescales. Simulations that include dark matter and feedback reproduce both channels. They grow halos, paint filaments, and measure dispersions like observers. The catalog statistics match sizes, shapes, and surface brightness trends. They also predict many ghosts hiding below current detection floors. Tiny tests drop surface brightness limits by 1 magnitude survey-wide. Your maps should bloom with dozens more powdery puffs per field. Rubin will push deeper, wider, and faster across the sky. Roman will sharpen low surface brightness imaging with stable, dark optics. Dragonfly keeps refining ultra-wide, glare-suppressed, telephoto mosaics. Weak lensing programs will stack millions more for average halos. HI arrays will map bigger, colder, fainter rotation fields. So the picture is simple: heavy halos are common, bright disks optional. As thresholds drop, theory and data should finally handshake cleanly. Expect catalogs to swell and outliers to clarify with context. The dark zoo gets names, addresses, and reliable family trees. That is when the real comparative anatomy begins in earnest. That ghostly smudge from the beginning now feels heavier, right? You can weigh it with motions and trace it with lensing. You can explain its darkness with tides, heating, and history. The light is shy, but the gravity is loud. That contrast is the trick these galaxies play so well. They turn the universe into a clean test of gravity. They also carry fossils from the first loud minutes. So, the immediate question becomes what new maps will reveal. Rubin, Roman, and Dragonfly should answer that with style. If you enjoyed this quiet cosmic weirdness, consider subscribing. Thanks for spending a few minutes under this very dark sky.